process is 2.1.2 AOI Design, which is circuit to truth tables to logic expressions. So really in this presentation, we are taking everything that we did with AOI Design in the last lesson where we worked with the truth tables and the logic expressions, and we are now going to use that to do circuit analysis. Specifically, we really have two different circuit analysis techniques. The first is that we take a circuit, or we have a circuit, and we then get the truth table and the logic expression from that circuit. And then the other method is that we extract the logic expression and then get the truth table. So it's either we get the truth table first or the logic expression first and then derive whatever we don't have. So in order to go from a circuit to a truth table to a logic expression, the process is that we look at a circuit and we add test points, or in our case, the digital probes in Multisim Live at the output of every gate, as well as the final output. We're then going to add a column to the truth table for every test point, and then working from the inputs to the output, we're going to complete the truth table for each test point, ultimately ending at the circuit's output. So from the completed truth table, we have to identify the minterms from the truth table anywhere the output is 1. And then using the extracted minterms, we then write the sum of products logic expression. So let's take a look at what that process looks like. So we're going to start with this circuit here, and we're going to walk through how we would complete this analysis. So we start by adding test points to the output of every gate. So test point 1, 2, 3, 4, and 5, those would be digital readouts in Multisim Live. We're obviously going to have a readout here as well, so we know what the final output of the circuit is. Then, once we've done that, we are going through the truth table. So we know that we have 3 inputs in this instance, and so we set up our truth table with function 1 being the last column. This would remain blank. We'd fill in the binary count here, and we would work through these settings. So at 0, 0, 0, what's happening at test point 1, test point 2, 3, 4, and 5. We know that 1 and 4 are giving us high, so that gets indicated, as well as the zeros. That final output would also tell us that it's a 0. So then we would continue 0, 0, 1, 0. We then would look at, well, we would know it's 0 at first, but we'd have all of our test points and continue. Ultimately, what we're going to be looking for is where we get highs at for function 1 is where we are going to have our minterms come from. We need to know what's happening with those test points, though, because that's critical in figuring out where input X is, where input Y is, and where input Z is. Because if you look back at this is labeled over here, but you're not going to have that necessarily. So we need to make sure that we are still identifying our test points so we know what's happening. Then once we have the extracted minterms, we're going to write the sum of products logic expression. So let's take a look at this example. Okay, you're going to analyze the logic circuit shown below to determine the truth circuit table. Okay, using the truth table, then we're going to derive the logic expression for output F2. So what you can do right now is take this circuit, pop it into Multisim Live, and practice with it. I'm going to give you some time to practice. let's take a look at the solution. Inside of Multisim Live, you should have put a test point after this inverter, after this AND gate, after this inverter down here, and before this AND gate, and then after this AND gate and before this OR gate. So that's where all of our test points should be. Our truth table should then have columns for test point 1, 2, 3, 4, and 5, as well as A, B, and C, and then function 2. After you've gone through and put the binary count in for A, B, C, and we've got the test points, we can then take a look at where we have the function as high and write our minterms, and then output our product of sum statement. So now if we go circuit to logic expression to truth table, it's a slightly different process. So working from the inputs to the output, we're going to write the accumulating logic expressions at the output of each gate, concluding with the expression for the circuit's output. And then using the circuit's output logic expression, we're obviously going to derive the circuit truth table. So we're going to look at this circuit, and it starts in a very similar way. So basically what we're doing here is after every gate, we're writing what this is. So because we start with X and this is an inverter, this becomes X naught. We then have Y feeding into this gate, which means the output from here is X naught Y. Coming up to the next gate, we know that we have X naught Y, and it is also coming from Z. So the output here is X naught Y Z. Down here we have an inverter coming off of Y, so we have Y naught. And then down here we have X, Y naught, because that is connected into this gate. And then into our final gate, we have our actual statement, which is X naught, Y, Z, or X, Y naught. So what this is saying is that F1 occurs when we either have X naught, Y, Z, or X, Y naught. So that's where we get our actual expression from. Now that we have that expression, we then build our truth table. So we have X, Y, and Z as our inputs and F1 as our output. We'll fill in our binary count just like we always do. And then we have to find the rows where we have X naught, Y, Z. And in that case, that's right here, so that gives us a 1. And then any row where we have X, Y naught. So we have 2 rows where it's X, Y naught right here and right here. So those are how, and then so those areas get 1s, everything else gets a 0, and our truth table is built. Okay, so now this is example number 2. I want you guys to walk through this process. You don't need Multisim Live for this one. You are just going to follow along with the inputs A, B, and C, and you're going to, and I highly recommend maybe screenshotting this and putting it into a Google Draw or some other application, or just redrawing it in your notebook so that way you can follow along. But at the output of every gate, you need to write the logic that's coming out of it until you get your final expression for F2. I'm going to give you a minute to work on this example, and then we'll go over the answer together. So what you should have gotten is, starting at the top from line A, this goes to A naught because that's an inverter. So this next gate is an AND gate, and that means coming from here to here, we then get A naught B. Following down along our logic trail, we then get A naught B C because we have C coming into this gate. Down here from the inverter right here, we have C naught. This then becomes B C naught because the other leg of this gate is connected to B. And then that goes into an OR gate, meaning we have A naught B C or B C naught is our final function statement. So then we create our truth table, A, B, C, and F2. We then have to use this expression to identify where we're going to have high signals. Okay, so we put in the 3 high signals, and then the rest get filled in with lows or zeros.